Okay, so we're still looking at inferences about, or inferences from two samples. And what we're going to do now is we're going to look at how to make inferences about two means when we have independent samples. So to start that discussion, we should probably look at the distinction between independent and dependent samples. Now, two samples are independent if the sample values from one population are not related or somehow naturally paired or matched with the sample values from another population. Now, two samples are dependent if the sample values are paired. That is, paired, sorry, that is, each pair of sample values consists of two measurements from the same subject. That's one way, such as before and after data, or each pair of sample values consists of matched pairs, such as pairs for husband and wives, where the matching is based on some inherent relationship that they have with each other. Okay? Now, let's take a look at these examples here, where we're asked to distinguish between independent and dependent samples. All right, the first one, home sales. Data set 23 in Appendix B includes list prices and selling prices for each of 40 randomly selected homes. So that's just like this case here, where it's kind of like before and after data. The list price is the price before you sell the house. The selling price is the price when you sell the house or after you sell the house. And these data are paired because we're talking about the same subject. We have 40 list prices and 40 selling prices, all for the same 40 randomly select houses. So those data values are definitely paired in a natural way. Now, here's the second one. On each of, oh, so this sample is dependent. I forgot to mention that. This sample is dependent. You can't say that these are not paired. All right, now, number 8. On each of 40 different days, the author measured the voltage supplied to his home, and he also measured the voltage produced by his gasoline-powered generator. One sample consists of voltages in his home. The second sample consists of voltages produced by the generator. Now, this, oops, I spelled dependent up here. That's dependent. All right, now, in this case, number 8, even though these voltages are collected on the same 40 days, there's no inherent relationship between the voltage at his house and the voltage produced by his generator. So there's no pairing of this data. So this sample is actually independent. So this is an independent sample. All right, now let's take a look here. Now, our objective in this section is to test claims about two independent population means. And also, we want to construct confidence intervals of the difference between two independent population means. So once again, we are going to create confidence intervals about a difference, and we're also going to do a hypothesis test about the difference. All right, so let's take a look here. These are some notations. For population 1, we have mu1. That's the mean from population 1. And we have the corresponding mean from population 2 being mu2. We have sigma 1, which is the population standard deviation for population 1. And we have sigma 2, which is the population standard deviation from population 2. We have N1, which is the sample size for the sample from the first population, and we have N2, which is the sample size from the sample of the second population. We have X bar 1, which is the sample mean of the first population, and X bar 2, which is the sample mean of the second population. We have S1, which is the sample standard deviation for the first population, and S2, which is the sample standard deviation for the second population. So the subscript tells you what population we're looking at. Okay, now requirements. Sigma 1 and sigma 2 are unknown, and it is not assumed that they're equal to each other. So not only do we not know sigma 1 and sigma 2, but we don't make the assumption that they're equal. Number 2, the two samples are independent. So we have to have independent samples. We just explained that a little while ago. 3, both samples are simple random sample. That seems to be always a requirement. Number 4, either or both of these conditions is satisfied. The two samples are large enough, which means N1 has to be greater than 30 and N2 has to be greater than 30. They both have to be greater than 30. And let's see. Or the other one is that both samples come from populations having normal distributions. So either we have a large enough sample or it's normally distributed. Those are just the criteria that we use for T. We're just now applying them to both populations instead of a single population. So this is going to be a T test statistic, and here it is. This is our test statistic T. And notice it says mu1 minus mu2. That's actually the parameter that we're testing, mu1 minus mu2. Notice it says mu1 minus mu2 is often assumed to be 0. So what we're going to be testing for the most part is that this part of this formula is 0. So let's go ahead and look at the degrees of freedom down here. Now, degrees of freedom, remember, whenever we use the t-test statistic, we have to tell how many degrees, we have to use a number of degrees of freedom. All right. When finding critical values or p-values, use the following for determining the number of degrees of freedom, denoted df. Although these two methods typically result in different number of degrees of freedom, the conclusion of a hypothesis test is rarely affected by this choice. So here are the two criteria. I'm going to use criteria number 1, which this is the most simple criteria, and it's also more conservative. And the degrees of freedom are just going to be the smaller of n1 minus 1 and n2 minus 1. So you subtract 1 from both sample sizes, and you take the one that is smaller. Now, the other way of calculating the degrees of freedom is given here. And we're not going to go into that one. We're going to use the first one. All right, the p-values, for the p-values, we're going to refer to table A3. All right, and that's the t-distribution table. And now, to do the confidence interval, remember here we said we're doing a confidence interval about the difference in the two population means. So that's the parameter that we're creating the confidence interval for. Not mu1 or mu2 separately, but we're actually creating a confidence interval for the difference. And the best point estimator for mu1 minus mu2 is x bar 1 minus x bar 2. That's the best point estimator. So all we have to do is find the margin of error and add it and subtract it to the point estimate. So we take the point estimate, we subtract E, we take the point estimate, and we add E. And here's how we find E. Okay, so let's go. Let's see. Here are the requirements for making inferences about means of two population where sigma 1 and sigma 2 are known. So up here, we had where sigma 1 and sigma 2 were unknown. That's what we're looking at here. Notice the requirement, sigma 1 and sigma 2 are unknown. Well, if we wanted to do this for sigma 1, where sigma 1 and sigma 2 were known, we would use a z-test instead, and this would be the z-test statistic. And this is how we would create our confidence interval. All the other information is exactly the same, except for the requirements up here. In the requirements, the two population standard deviations have to be known. Now, let's take a look at some examples. Oh, actually, here's how we're going to make our decision of what test to use. First, you start and ask yourself, are sigma 1 and sigma 2 known? Then we would use the normal distribution. That's the thing we were just looking at. If your answer is no, then can you assume that sigma 1 and sigma 2 are equal to each other? For the most part, that answer is going to be no, so we're not going to use this pooled estimate. And in our course, we're going to forget about the pooled estimate. All right, so let's take a look down here. All right, so now we're down here and it says, assume that the two samples are independent, simple random samples selected from normally distributed population. Do not assume that the population standard deviations are equal unless your instructor stipulates otherwise. I am stipulating otherwise. I am not stipulating otherwise. I do not want you to assume that the two population standard deviations are equal. I do not want you to make that assumption. All right. So let's go ahead and look at this. The number 11, the mean tar content for a simple random sample of 25 unfiltered king size cigarettes is 21.1 milligrams with a standard deviation of 3.2. So this standard deviation is coming from this sample of 25 unfiltered cigarettes. So I do not know the population standard deviation. So I'm not going to use Z, I am going to use T. And let's see here. We have another simple random sample of 25 filtered 100 millimeter cigarettes, and their mean tar content was 13.2 also. Oh, sorry, was 13.2, and the standard deviation was 3.7. So we have mu one, we have x bar 1 and x bar 2, S1 and S2. Construct a 90% confidence interval estimate for the difference between the mean tar content of unfiltered king size cigarettes and the mean tar content of filtered king size cigarettes, or filtered 100 millimeter cigarettes. Does the result suggest that the 100 millimeter filtered cigars have less tar than unfiltered king size cigarettes? Well, let's see. They've given us a few numbers here. They gave us a sample size of 25. So let's say N1 is equal to 25. Let's see. We also have 21.1 milligrams for the average, for the mean. So X bar 1 is equal to 21.1. And the standard deviation is 3.2. So S1 is equal to 3.2. We also have N2, and it says that N2 is 25 also. And the mean is 13.2. So X bar or 2 is 13.2. And the standard deviation, S2, is equal to 3.7. So I have N1, X1, N1, X bar 1, and S1, N2, X bar 2, and S2. All right, construct a 90% confidence interval. So the confidence level is equal to 90% or 0.90. That's confidence level. Construct a 90% confidence interval. Estimate of the difference between the mean tar content of unfiltered cigarettes and the mean tar content of the 100. All right, so let's go ahead and construct our confidence interval. And to construct the confidence interval, we're going to follow the directions here for our TI 83 plus. So let's bring that guy in here. Okay, and what it says here is that, let's clear this out. We need to go to stat. So we go to stat, right? Then we go in stats, we go over to tests. So we click over, scroll over to tests. And since we're doing an interval, we're going to do 2samp t int. So that's a 2 sample t interval, right? That's number 4. 2samp, no, that's the test actually, sorry. We're doing 2samp t interval, which is actually number 0, 2samp t int. When we press enter, it asks us if we have data or statistics. We have statistics. We go down and it asks for x1. X1 we saw down here was 21.1. Let's go scroll down a little bit. X1 was 21.1, so we'll type that value in, 21.1 for x bar 1. S1 was 3.2, 3.2. N1, let's see, N1 is 25. X bar 2 was 13.2. 13.2. S2 was 3.7, and N2 is 25. All right, so I have all those, and then the confidence level. The confidence level that we have is a 90% confidence level, 90. And it asks us whether it's pooled or not. We're going to say no, it's not pooled. And in our course, you will always answer this particular question no. All right, so never answer the question pooled with yes, and then go to calculate. And it thinks for a while, and then it gives us this confidence interval. So let's see. So for number 11, our confidence interval is actually 6.26 to 9.54. 9.54. And that second question says, does the result suggest that the 100s the 100 millimeter filtered cigarettes have less tar than the unfiltered king size cigarettes? Well, yes, there is definitely a difference because this confidence interval does not contain zero. So there's a positive difference, meaning that the first population has a mean tar content larger than the second population. Now, number 12 is going to ask us to test that as a hypothesis. So it says refer to sample data in exercise 11 and use the zero point zero 0.05 significant a zero point zero 0.05 significance level to test the claim that the unfiltered king size cigarettes have a mean tar content greater than the filtered 100s. What does this suggest about the effectiveness of cigarette filters? Let's go ahead and do that. Notice the significance level is different here. Up there I wanted a 90% confidence, which was an alpha of 0.10. Down here I want a alpha of 0.05. So the significance level is slightly different here. All right, so let's see. Let's get rid of this information here. That's the sample data information, so let's keep that. And let's bring back in our... Actually, let's come up with our null and alternative hypothesis first. So let's see. So it says we want to test the claim. Well, alpha first. Alpha is 0.05. And the claim is that the unfiltered king size cigarettes have a mean tar content greater than the filtered 100s. So the kings are actually sample 1 and the filtered ones are actually sample 2. So these are the ones with these are the unfiltered ones, unfiltered, and these are the filtered. So what they're saying is that the mean from population 1, the unfiltered, is greater than the mean from population 2, the filtered. That's what this claim is. They claim that the unfiltered have a mean greater than the filtered. So basically, the claim is that mu1, the mean for the unfiltered, is greater than mu2, the mean for the filtered. And this, by default, because it does not contain equality, is the alternative hypothesis, which means the null hypothesis is that there's no difference between filtered and unfiltered cigarettes, mu2. All right, so this one here is our claim, and these are our two hypotheses, null and alternative. All right, so let's go ahead and run our hypothesis test. So we pull out the TI-83, we turn it on, clear. Now we're going to go back to stats. We're going to go over to tests, and in this case, instead of doing the two sample t interval, we're going to do the two sample t test. Number 4. Number 4 is two sample t test. So I press enter, and it's going to ask me if I have statistics or data. So I go down and I give it my statistics. All my statistics here are already correct. 21, because I just did this for the confidence interval. So all these numbers are still in the calculator. 13.2, 3.7, uh, and 2 is that. Now the alternative hypothesis. The alternative hypothesis is that mu1 is greater than mu2. So mu1 is greater than mu2. So I'm going to go over and select greater than mu2 and press enter. And then I go down, pooled, no once again, and we hit calculate. And it comes back with this. This is our test statistic. So the t-test statistic here is 8.07. The p-value, that's a scientific notation number. That's a decimal point, 10 zeros, and then, actually, yeah, decimal point, 10 zeros, and then a 9.8. That's a very, very small number. So definitely we're going to reject the null hypothesis here. And the degrees of freedom, uh, well, that was calculated using the formula we showed up top. And all the other information is stuff we already know. All we're really concerned with is the test statistic and the p-value. We need the test statistic if we're going to do the traditional method, because we're going to compare that to our critical values, which we'd find from the table A3. But the p-value method is what we're going to use. So the p-value here is, like I said, very, very small. So let's do our conclusion here. The p-value in this case is a very small number. I'm going to write it in scientific notation. The p-value is 9.8 times 10 to the negative 11th power. That's what the calculator was telling me. That's a very, very, very small number, and that is less than alpha, 0.05. So since the p-value is so low, the null must go. You remember that? So the p-value leads us to rejecting the null hypothesis. Reject null hypothesis. And since we're rejecting null hypothesis, well, we're rejecting this hypothesis in favor of the claim. So there is sufficient sample evidence to support the claim that unfiltered cigarettes have a tar content greater than filtered cigarettes.